All right, so I wanted to use a more traditional way to also solve number 6. So for the same problem, all right, there's your ramp, 35-degree angle, and this is still going to be the mass of object A, which we're told is 200 Newton weight, right? And then we have a pulley, string, and then this would be object B, right? And force diagram's not going to look any different, not that exciting. I got weight of object A. I got the tension going up the ramp parallel to the surface. I got my normal force perpendicular to my tension, okay? And now I should draw some nice reference lines, right? So I'll draw some reference lines. That should help. Okay. There's another reference line right there. All right. Let's see if this is my eraser. Oh, wow, that's a huge eraser. I didn't want to erase all that. That was crazy. That's pretty funny. Maybe I should make the eraser smaller. What do you think? Maybe I'll make it like this. There we go. That's much nicer. All right. So there's my, just making a reference line there. Okay. And then I'm going to also want to make this a reference line. And again, as I said before, your reference lines are key because they help you to check your work. Draw lots of them. They're your friend. Okay. So let's see. It looks like this is 35 degrees. This is 35 degrees. This is 35 degrees. And that's 35 degrees. And that's no different than the other force diagram I showed you. Okay? Where this approach is different is now I'm going to draw an axis-only force diagram. So I'm not going to mess with my force diagram. I'm going to leave it as is. But I'm going to draw a separate axis-only force diagram. And I'm going to define a coordinate system. So I'm going to make this direction here my y direction. And I'm going to make this direction here my x direction, okay? So I've defined my x, y direction, right? So now what I'm going to need to do, I'll just extend this reference line down. That's how I like to do it. There's a lot of ways you could do this, but this is just my preference. I just extend that down, and then I'll draw a perpendicular to that. The perpendicular looks kind of sloppy, but I'm trying here. And then I'll draw an up. I'm just trying to copy my reference lines. You think a ruler would help here? I think so. Like a see-through ruler? You need to get one of those, okay? Get a see-through ruler for the AP test and just for my class in general. So I've defined this way as my positive y direction. I've defined that way as my positive x direction, right? And we don't care in physics that when we tilt our coordinate system. In fact, we do it all the time. Now, based on this tilted coordinate system, this is called an axis-only force diagram. Okay? Although, I mean, this is a very traditional technique. I don't like this technique so much, but it works, and it's very traditional. There are some problems where this technique may work better, but I haven't found any yet. No, just kidding. I tend to go to the other vector sum diagram. But anyway, this is a force diagram, and this is just a plain old diagram. Okay? So all the forces that already lie along my xy axis, I'm just going to keep them. So I got tension, which is already along my x-axis. I got normal, which is already along my y-axis, right? So that one's fine. Cool? Okay, I'm going to need to fix that. Sorry about that. I can draw nicer. There, normal. Okay, now the real problem is my weight. My weight does not lie on my x or my y-axis. So what I'm going to do is I'm going to extend these down lower so that I can draw a little trigonometric window. All right? So I'll do this in another color. So there's my weight going down, right? That's my weight. Now, my weight consists of two vectors. I have a vector in the y direction. It's actually negative y, but that's okay. So this is my weight component that's in the y direction along the y-axis. And this would be parallel to my x-axis. So these are my x, y components of my weight, all right? And I can pretty easily see from all my reference lines that this has to be 35 degrees right there. So that tells me that, let's see, weight. I like to look for the opposite side as the angle I know. And I immediately go to that side and say, well, Wx is going to be W sine 35 degrees. And you can look at the other screencast for more detail there. And W in the y direction is going to be the same exact thing except cosine. So that's my shortcut. You shouldn't do that shortcut until you're comfortable with sine and cosine. But again, the way I do it is I identify my angle correctly, then I look at the side opposite, and I know that that opposite side is going to be my sine. The adjacent side is going to be my cosine. Okay? So WY is my adjacent side. That's going to be cosine. And I'm going to have to, of course, multiply by the hypotenuse. Okay? So my WY, I'm just going to copy it over here. So I'm literally replacing my weight vector with my weight that's in the y direction and my weight which is in the x direction. And the logic, I imagine, is that WY and WX, these components add to my weight vector. So W in the x direction plus W in the y direction equals my weight vector. These are called component vectors. So I'm replacing my weight with its components. It's a component vectors that add to it. So it's like saying, it's like replacing 4 with 3 plus 1, right? But these are vectors, not numbers. So, and I can also see readily that now when I use Newton's first law, I have to actually use it in along both axes. So I'm going to add the forces in the x direction. And those forces must add to 0 since our acceleration in the x direction is 0. Okay, so now I'm going to proceed to add the forces in the x direction only. So I got tension, positive, right? And I'm going to add that with my weight in the x direction component, which is negative direction. Okay, so what this technique allows you to do, which is actually a very clever and brilliant technique, is it allows you to treat the vectors as scalars because you're using plus and minus to account for their direction. Okay, so this is telling me that tension has to equal my x component of the weight, which is going to be, okay, it looks like I was sloppy here. This is WA, and this is WA, WA. Okay, so my tension has to equal my x component of the weight, which is the weight of object A times the sine of 35 degrees, right? So that's what the x-axis has taught me, okay? And this is going to help me because for system B, again, everything over here was for system A. For system B, my force diagram is much, much simpler. I just have tension going up, and I have the weight of system B going down. And I can use the same method. Why don't I make up? Actually, you know what? I'm going to be consistent here. Let's make down positive so that I'm consistent. In other words, that way is positive. Okay? For system A, this is positive, but for system B, down is positive. So by that logic, if I add the forces along this, I don't know, I'm going to just call it a positive x-axis, and I'm going to call this positive x-axis too. So I'm making a consistent x-axis that applies to both systems. All the pulley does is change the direction of a force. So if I add the forces along this x-axis that I have defined, you're going to see that, again, these have to add to 0 because acceleration in that x-axis is 0, right? So when I add those, what I'm going to see is that positive tension, nope, I did that backwards, sorry. So I'm going to see that the weight of object B, which is positive, adds with my tension, which is negative, to give me 0. That means that tension has to equal the weight of B. Now, it might seem silly, but for the harder problems that are more complicated, being methodical like this is going to help. Okay? So if tension equals weight of B here, right? If I learn that from system B, well, since system A and B both are pulled by the same rope, that means that, let's see here, both tensions, the tension on system A's force diagram and the tension on system B's force diagram, that's the same tension, right? So just like the prior problem, since I've solved for tension here, I can now say that W, weight of object A, times sine 35 degrees, that has to exactly equal the weight of object B. And if you'll notice, this is exactly the same solution we had before. So I don't think I really need to go into it. You could see that now it'll be pretty easy. You can just substitute mass of A, G, sine 35 equals the mass of system B times G. G's, if you divide both sides by G, it cancels out of this equation. And you've got a solution for the mass of object B, right? So the mass of object B is going to be the mass of object A, sine 35 degrees. Now, so that answer is part A. Part B is sort of the more interesting part, I think. The other thing that we do, since you added the forces in the x direction for system A, you better add the forces in the y direction and see what that can tell you. And the forces in the y direction also have to add to 0, since there is no acceleration in that y direction. So you're literally using n1 along both axes. Okay? In the y direction, we have normal that's added to wy, which is in the negative direction. And those have to add to 0. That implies that normal has to equal in magnitude to wy, and wy is wa cosine 35 degrees. Okay? And that's going to simplify to mass of object A times G times cosine 35 degrees. So we've solved for normal force, we've solved for tension, and we've even found the mass of object B. This is a slightly different technique. This is a more traditional technique. Both techniques are quite powerful for solving a variety of problems. Anyway, I hope you like it. Hope it helps you figure something out. And have a good day. Thanks for watching.